Welcome to the Deep Dive. Ready to explore the evolution of codes and their impact on computers and communication?
Oh, absolutely.
We've got an amazing book on computer hardware and software as our guide.
Yeah.
And trust me, it's packed with aha moments. We're talking Morse code, Braille, even cat adoption.
Wow. That's quite a range.
It is, right? Get ready to see them all in a whole new light.
Oh, intrigued already.
So let's kick things off with Morse code. Dots and dashes, simple enough, right?
Yay.
But back in the day, what were its limitations?
Well, imagine trying to have a Morse code conversation across a crowded room.
Yeah.
It just wouldn't work.
Too much interference.
Yeah, exactly. Over short distances with a clear line of sight, it was fine.
Right.
But anything more than that, and you needed something else.
Enter the telegraph. Wires and electricity to the rescue.
Right.
It's like the supercharged Morse code.
Absolutely.
But did they ever worry about messages getting garbled in transmission?
Oh, definitely. Reliability was a huge concern back then. Even Paul Revere's lantern system during the Revolution had a clever trick for error correction.
Really?
Yeah. One lantern meant land invasion, two meant sea invasion.
Interesting.
By not having a signal for no invasion, they made the system more robust.
Clever. So even back then, they understood the importance of redundancy.
Absolutely. It's a fundamental principle of reliable communication.
That's fascinating.
Yeah.
Now let's switch gears to Braille.
Okay.
I never thought of it as a code with error correction built in.
Oh, it's incredibly ingenious. Each character uses a 6-dot cell.
Right.
But Louis Braille, the inventor, intentionally didn't use all possible combinations for lowercase letters.
So he built in redundancy from the start.
Exactly. This meant that even if a dot was faint or misplaced, the reader could still decipher the letter.
That's brilliant. Okay, now for a real curveball.
Yeah.
How does cat adoption connect to computer science?
All right, so picture this. You're at a shelter, tons of cats, and you're looking for your perfect match.
Okay, I'm with you.
You have specific criteria.
What sort?
That's where Boolean logic comes in. It's all about using and, or, and not to make decisions.
So finding the perfect cat is actually an exercise in logical operations.
Precisely. You might say, I want a cat that's black, Andy, playful, or a cat that's fluffy, Andy, good with kids.
That makes sense. But how does this relate to computers?
Well, this is where it gets really cool. Boolean logic is the foundation of digital logic, the way computers make decisions.
Okay.
Each of those and or not operations can be represented by physical circuits called logic gates.
So those simple statements we use to find a furry friend are actually the basis for how computers think.
Exactly. It's all about manipulating those logical operations to perform calculations.
Amazing. Now let's talk about relays.
Okay.
They were using telegraphs, but then they became something even bigger, right?
Oh, absolutely. Relays were crucial in creating those logic gates we just talked about.
I see. So they were the physical embodiment of those logical operations.
Exactly. You had AND gates or a gate gates and not gates, all thanks to relays.
So relays were like the missing piece that allowed us to build those logic gates leading to the computers we have today.
Right.
Starting to see how all these seemingly disparate pieces fit together.
It's all connected.
Now let's talk about binary numbers, the language of computers.
Okay.
It's all zeros and ones, but how does that actually work?
Think of it this way. Each 0 or 1, which we call a bit, is like a switch, either on or off.
Okay.
And by combining these bits, you can represent any number.
It's different from our decimal system, but it makes sense for computers.
Right, because their circuits are essentially just a bunch of on-off switches.
So all the complex stuff computers do boils down to manipulating those ones and zeros.
Pretty much. It's the foundation of digital computation.
That's wild. But how do computers represent text? We've got Morse code, Braille, but what about regular words?
That's where coding systems like ASCII and Unicode come in.
Yeah.
ASCII uses 7 bits to represent letters, numbers, and punctuation.
Got it.
It worked great for English, but it couldn't handle characters from other languages.
So ASCII was like a language barrier for computers.
You could say that. It limited their ability to communicate across different writing systems.
And then came Unicode, right, to save the day.
Exactly. Unicode is a massive system that aims to represent every character from every writing system.
Wow, that's ambitious.
It is. And it uses clever encoding schemes like UTF-8 to do it efficiently.
So Unicode is like the Rosetta Stone of the digital age, breaking down those language barriers.
That's a great way to put it.
Now, before we move on, our source mentions half adders and full adders. What are those all about?
Those are fascinating. To understand them, we need to think about how computers add.
Okay.
It all starts with binary addition.
Right, where you add 2 bits together.
Exactly. So 1 plus 1 in binary would be
10. I remember that much.
You got it.
Yeah.
And just like in decimal addition, you carry over the 1.
Right.
A half adder is a simple circuit that can add 2 bits and produce a sum and a carry bit. But for adding numbers with multiple bits, you need a full adder, which can handle those carry bits more effectively.
So it's like the half adder is the rookie, and the full adder is the seasoned pro.
Haha, I like that analogy.
And just think, to build an 8-bit adder using those old-school relays, you'd need 144 of them.
Can you imagine?
Talk about a noisy computer. But it really highlights how much ingenuity went into those early computing machines.
It really does.
Speaking of which, let's talk about the pioneers who laid the groundwork for all this. Our source starts with analog computers, like the differential analyzer.
Oh yes, the differential analyzer. Picture a giant machine, room-sized, with spinning disks and gears.
It sounds intense.
It was. It could solve complex equations, but it was all mechanical.
Wow.
But then came Charles Babbage, a true visionary with his analytical engine.
Now, Babbage, he was way ahead of his time, wasn't he?
Oh, absolutely. His analytical engine was essentially a blueprint for the modern computer.
Really?
It had a store, like memory, and a mill that performed calculations.
So it wasn't just a number cruncher.
Yeah.
It could actually be programmed.
Exactly. It was designed to be instructed to perform different operations, a revolutionary concept.
That's incredible.
Yeah.
But it never actually got built, right?
Sadly, no. The technology of his time wasn't advanced enough.
But his ideas lived on.
Oh, absolutely. He planted the seeds for the digital revolution.
And those seeds blossomed with the invention of the vacuum tube.
Right. Suddenly we had electronic computers like the ENIAC.
Ah, the ENIAC. Wasn't it massive?
Oh, it was enormous. 18,000 vacuum tubes weighed about 30 tons.
Wow, that's hard to even imagine.
It was a true behemoth.
And then came the transistor, right. Much smaller, more efficient.
The transistor was a game changer. It revolutionized electronics, allowing for miniaturization.
Right, and that led to integrated circuits, putting multiple transistors on a single chip.
Exactly. It was the birth of the computer on a chip.
It's mind-boggling how far we've come from those room-sized behemoths to the powerful devices we have today.
It's incredible, isn't it?
But let's rewind a bit and talk about computer memory. RAM versus hard drives. What's the difference?
Well, think of RAM, or random access memory, as your computer's short-term memory.
Okay.
It stores data that the CPU is actively working with.
Right.
Hard drives and SSDs, on the other hand, are like long-term storage.
So RAM is like a whiteboard where you jot down notes, and a hard drive is like a filing cabinet where you store important documents.
Exactly. A perfect analogy.
But the organization of RAM itself is fascinating.
It is. Imagine a grid of memory cells, each with a unique address.
Okay.
To access a specific location, the CPU uses decoders and address lines, kind of like a postal worker using a zip code.
So there's a whole system for finding and retrieving data within that memory grid.
Yes, it's remarkably organized at such a tiny scale.
It's amazing. But how does the computer manage all these different parts? That's where operating systems come in, right?
You got it. An operating system like CP/M or MS-DOS is like the conductor of an orchestra.
So it's the software that keeps everything running smoothly.
Exactly. It manages the computer's resources, ensuring everything works together.
It's a pretty important job. And our source mentions device independence as a key innovation.
Oh, that was huge. It meant that software could be written without needing to know the specifics of the hardware.
So you could write a program once, and it could run on different computers with different hardware.
Precisely. It was a game changer for software development.
And speaking of game changers, let's talk about the personal computer revolution.
Ah, yes. When computers moved from labs and offices into our homes,
It's hard to imagine a world without them now, but what made them so revolutionary?
personal computers democratized access to computing power, opening up a world of possibilities.
It wasn't just about having a computer, it was about what you could do with it.
Exactly. We saw groundbreaking applications like VisiCalc, the first spreadsheet program.
This is a calc, huh?
It took advantage of the personal computer's capabilities to create a dynamic and interactive way of working with data.
So it was like a catalyst for the personal computer revolution.
In many ways, yes. It showed the world what personal computers were truly capable of.
It's amazing how something as seemingly simple as a spreadsheet could spark such a revolution.
It really is. But before we delve further into software, let's circle back to how we communicate with computers.
Okay.
We've talked about binary numbers, but how do we actually give instructions to a machine?
Is that where assembly language comes in?
You got it. Assembly language is a low-level programming language, very close to the CPU's architecture.
So it's like speaking the computer's language, but in a way that's at least somewhat understandable to humans.
Exactly. But even assembly language can be quite complex, especially as computers become more sophisticated.
Right, so that's where high-level programming languages come in, right?
Exactly. Languages like Fortran, COBOL, BASIC, C, and Python.
Those are more human-readable, right?
Much more. They allow programmers to express instructions in a more abstract and intuitive way.
It's like having a translator between humans and machines.
A perfect analogy. But these high-level languages still need to be translated into machine code, right?
The language the computer actually understands.
That's where compilers and interpreters come in.
Ah, yes, the language specialists.
You could say that. A compiler translates the entire program at once, while an interpreter translates and executes it line by line.
So a compiler is like having a chef who can take a complex recipe and turn it into a delicious meal the computer can digest.
Haha, I love that analogy. And the development of high-level languages and compilers was essential for making programming more accessible.
It's fascinating how we've built this whole system for communicating with computers.
It's a testament to human ingenuity.
And speaking of ingenuity, our source actually walks us through a simple JavaScript program.
Oh, yes. JavaScript.
I know it's used for websites, but I didn't realize it was so versatile.
It is. It can be used for server-side programming, mobile apps, even game development.
That's impressive.
It really is.
And the example in our source, which calculates the sum of numbers from 1 to 100, is surprisingly easy to follow.
It's a great introduction to basic programming concepts.
This deep dive is really opening my eyes to the world of coding. But let's switch gears back to numbers for a moment.
Okay.
We've talked about integers, but how do computers handle decimals?
Ah, that's where floating point numbers come in.
Floating point numbers.
Yes. They're essential for scientific and engineering applications, where you need to represent numbers with fractional parts.
So it's like having a special type of number for really precise calculations.
Exactly. And they're represented in a clever way, using a system of sign, exponent, and significant.
Sounds complicated.
It is, but it allows computers to handle a wide range of numbers with incredible accuracy.
That makes sense. And back in the day, programmers had to write their own routines for these calculations.
They did. But eventually, specialized hardware called floating point units, or FPUs, were developed.
So like having a team of mathematicians built right into the computer chip?
Precisely. It made those calculations much faster and more efficient.
It's amazing how much thought and ingenuity has gone into every aspect of computer design.
It really is.
But speaking of handling data, let's talk about the internet.
The internet.
This vast network that connects computers worldwide.
Yes.
How does it actually work?
Well, the internet relies on a concept called packet switching.
Packet switching.
Imagine you're sending a letter, but instead of sending the whole thing, you divide it into multiple postcards.
It's like a digital relay race.
Exactly. Each packet carries a piece of the message and travels independently across the network.
But how do those packets know where to go?
That's the job of routers.
Routers.
They act like intelligent traffic controllers, directing the flow of packets.
So they're constantly making decisions, ensuring that all those packets reach their destination.
Exactly. It's a dynamic and complex system.
It's mind-blowing how we can send information across the globe in an instant.
It really is. And that's what has enabled the creation of the World Wide Web.
The World Wide Web, the source of so much information and entertainment.
It's transformed our world.
It has. Our source mentions HTML, HTTP, and URLs, all those acronyms that make up the web's foundation.
Right.
Can you break those down for us?
Of course. HTML, or Hypertext Markup Language, is the language used to create web pages.
Okay.
It uses tags to structure the content and define its appearance.
So it's like the blueprint for a website.
Exactly. Then you have HTTP, or Hypertext Transfer Protocol, which is the language browsers and web servers use to communicate.
Like the protocol for sending and receiving web pages.
Precisely. And finally, URLs, or Uniform Resource Locators, are those web addresses we use.
So it's like a street address for a website.
A perfect analogy. It's how we find specific pages on the vast web.
It's amazing how these technologies have become so integral to our lives.
It's incredible how far we've come from those early days of computing.
This deep dive has been an incredible journey through the world of codes and computers so far.
It has, and we've only just scratched the surface.
There's still so much more to explore.
Absolutely. And the story is far from over.
Well, That's a great place to take a break.
Okay.
We'll be back soon to continue our exploration of codes, computers, and the digital world.
Sounds good. It's true. The internet, while revolutionary, it's like this double-edged sword, you know?
How so?
Well, think about it. It's like suddenly having access to every book ever written,
Yeah.
but with no real way to organize it all.
So it's not just about the information. It's
Yeah.
about making sense of it all.
Exactly. Filtering out the noise, finding what's relevant, that's a whole other challenge. And that's where those early ideas about a world brain,
Right.
those become even more relevant, I think.
Because they weren't just about collecting information.
No.
They were about making it meaningful. Right.
Exactly. Organizing it, connecting the dots.
So the challenge now is less about having information
Right.
and more about having the right tools to navigate it all.
Absolutely. And that brings us back to those underlying systems, those codes.
The ones we've been talking
Yeah.
about.
Yes. They're the invisible threads that hold everything together.
It's like we've been so focused on the content, we've forgotten about the structure underneath.
In a way, yeah. And that structure is constantly evolving.
Always changing.
Yeah, it's this dynamic interplay between hardware, software, and the brilliant minds pushing the boundaries.
Speaking of brilliant minds, I'm curious about those early programmers, the ones who worked with assembly language.
Oh, they were the pioneers, the real trailblazers.
It sounds incredibly complex.
It was. Imagine writing instructions using these cryptic codes
Yeah.
that directly manipulate the computer's hardware.
Wow.
It required incredible precision, patience, and a deep understanding of how computers work at the most fundamental level.
It's like they were digital architects.
Yeah.
Meticulously crafting each line of code.
It's a great analogy. But as software became more complex, the limitations of assembly language became apparent.
How so?
Well, writing large programs in assembly language was incredibly time-consuming
Yeah, I can imagine.
and error-prone. And it required a level of specialized knowledge that not all programmers had.
So it was like trying to build a skyscraper using only hand tools.
Exactly. And that's where those high-level programming languages came in, like a breath of fresh air.
Ah, yes.
Yeah.
Fortran, COBOL, BASIC.
They offered a more abstract way to write instructions, more human-friendly.
Right, like switching from hand tools to power tools.
Exactly. And then compilers came along, further accelerating the evolution of programming.
Those software tools that translate high-level code into machine code.
Yes. They were like interpreters between humans and machines, bridging the gap between our intuition and the computer's precise language.
It's incredible how we've developed this whole system for talking to computers.
It's truly remarkable.
And speaking of remarkable, the JavaScript example in our source really shows how versatile programming languages can be.
Oh, JavaScript is a powerhouse.
I always thought it was just for making websites interactive.
It started that way, but it's evolved so much. Yeah. Now it's used for server-side programming, mobile apps, even game development.
That's amazing. Like a Swiss Army knife for programmers.
A great analogy. And it highlights the power of clear, well-defined codes and languages.
The foundation of communication, really.
Absolutely. Whether it's between humans and computers or between computers themselves.
Which brings us back to the internet, right? That vast network where computers are constantly talking to each other.
Exactly. And at its core, the internet is all about information exchange.
Sending and receiving data.
Right. And that requires a robust system of codes and protocols to ensure everything runs smoothly.
Our source talks about packet switching and routers as key elements of this system.
Oh, they're essential. Packet switching is like taking a letter and dividing it into multiple postcards.
Right, we talked about that earlier, the digital relay race.
Exactly. Each packet carries a piece of the message and travels independently across the network.
And routers are like the traffic controllers along the way.
Precisely. They analyze the destination addresses and figure out the most efficient route for each packet.
So they're constantly making decisions, directing the flow of data.
Yes, it's a dynamic and incredibly complex system.
It's mind-boggling to think about the scale of it all.
It really is. Billions of packets of data traveling the globe every second.
But how do they actually get transmitted? Our source mentioned modems, but I'm not sure I fully understand what they do.
Well, modems are the translators.
Translators.
They take digital data, the ones and zeros, and convert it into signals that can travel over telephone lines or cable networks.
Ah, so they're like the bridge between the digital world and the physical world.
A great way to put it. In the early days, those dial-up modems, you could actually hear them working.
I remember those days. The screeching and beeping.
It was a symphony of digital communication.
And then came broadband, right? DSL and cable internet.
Much faster speeds, no more waiting forever for a web page to load.
It's amazing how far we've come.
It is. And with fiber optics, we're pushing those speeds even further.
It's like we've gone from riding a bicycle to flying a supersonic jet.
A perfect analogy. But amidst all this talk about data transmission, it's important to remember that the information itself needs to be encoded and decoded.
Right, in a way that both computers and humans can understand.
Exactly. And that's where those coding systems we talked about, like ASCII and Unicode, come back into play.
So it's all about having a common language for text, a universal code that everyone can understand.
You got it. It's essential for ensuring that messages are transmitted and interpreted correctly, no matter the language or operating system.
It's like having a global dictionary for digital communication.
Exactly. And it highlights the importance of those standards and protocols that underpin the internet.
The rules of the road, so to speak.
Precisely. Without them, it would be chaos.
It's like trying to have a conversation in a room full of people speaking different languages. You might get by with some basic gestures, but that's about it.
A great analogy. And it makes you appreciate the work of those early pioneers who established these foundations.
The ones who created these systems that we often take for granted.
Yes. They laid the groundwork for the digital world we live in today.
Speaking of those pioneers, our source mentioned H.G. Wells and his vision of a world brain.
Ah, yes, the world brain, a vast repository of human knowledge accessible to everyone.
It's amazing how that vision has come to fruition with the internet and the World Wide Web.
It really is. The World Wide Web, with its interconnected web pages and hyperlinks, it's revolutionized the way we access information.
It's like having a library at our fingertips.
Exactly. But as we've discussed, it's not without its challenges.
Right, the sheer volume of information can be overwhelming.
It can. And then there's the issue of misinformation, filtering out the noise, finding what's reliable.
Those are big challenges.
They are. And that brings us back to those early visions of a world brain or a memex.
Right, because it wasn't just about collecting information, but about organizing it, making it meaningful.
Absolutely. We need the tools and skills to navigate the sea of information effectively.
It's like having a vast library, but without a proper cataloging system.
A great analogy. We need ways to sift through the information, identify reliable sources, connect ideas in meaningful ways.
And that's where things like search engines and artificial intelligence come in, right?
Exactly. They're helping us make sense of the digital world, but we still have a long way to go.
It's an ongoing challenge, one that requires ongoing innovation and collaboration.
Absolutely. And it requires us to be more discerning, more critical in how we consume and share information.
This deep dive has really opened my eyes to the complexities of the internet.
It's a fascinating and ever-evolving landscape.
And it's made me realize that simply having access to information isn't enough. We need to develop the skills to use it wisely and responsibly.
I couldn't agree more. It's a responsibility we all share.
Well, I think we've covered a lot of ground in this part.
We have. It's amazing how these seemingly simple concepts like codes and binary numbers have led to such a complex and interconnected world.
It really is, and I'm sure there's still so much more to uncover.
Oh, absolutely. The story of codes and computers is far from over.
It's amazing, isn't it, how these simple ideas like codes and binary numbers have led to such incredible technology. It's like we've cracked the code of the digital world.
It is pretty remarkable. And what's fascinating is how those early visions, like the world brain, are becoming more and more relevant today.
Right, as we deal with information overload and the need for better tools to navigate it all, it makes you wonder, what's next for codes and computers? What new languages and technologies will we see?
Well, that's the exciting part. We're on the verge of some major breakthroughs. Think artificial intelligence, quantum computing, biotechnology.
It's both thrilling and a little daunting, right? To imagine what the future holds.
I agree. But as we've learned in this deep dive, understanding the past can help us navigate the future.
Right. By tracing the evolution of these technologies, we can get a better grasp on the principles that drive innovation.
Exactly. Logic, efficiency, the pursuit of knowledge, those will always be important.
This deep dive has been quite a journey. From simple dots and dashes to the complexities of the internet, we've covered a lot of ground.
We have, and I think it highlights how those foundational concepts of codes and binary numbers are woven into the fabric of our digital lives.
Absolutely, it's all connected, and really speaks to human creativity, our desire to understand and shape the world. But amidst all this technological progress, it's important to remember the human element.
I agree. Technology is a tool, and it's up to us to use it wisely.
Which brings us back to those challenges that we discussed. Information overload, misinformation, the ethical considerations.
Those are critical issues that we need to address head on.
Right. We need to cultivate critical thinking skills, promote digital literacy, and have those tough conversations about the impact of technology.
It's like we've been given this amazing toolbox, but now we have to learn to use it responsibly.
Exactly. This deep dive has really made me appreciate the complexities of the digital world and how crucial it is to understand these technologies. How about you? Any final thoughts as we wrap up?
For me, it's the realization that codes are more than just technical tools. They're expressions of human ingenuity.
I like that. They're bridges between our minds and the digital realm, shaping the future in ways we're only beginning to understand.
It's a future full of both incredible potential and very real challenges.
A future we have a responsibility to shape. Well, this has been an amazing journey, and I hope our listeners have enjoyed diving deep into the world of codes, computers, and communication. We've only scratched the surface, but it's a great starting point.
It is. Keep exploring, keep learning, keep questioning.
The digital world is constantly evolving, and it's up to us to stay engaged and informed.
The future of technology isn't set in stone. It's being written right now by the choices we make today.
That's a great point. Well, on that note, thank you for joining us on this deep dive. Until next time, keep those curiosity circuits firing.